Let me tell you something. Somebody once asked me a simple question. They said, "Richard, why do magnets attract each other?" And I gave them what might have been the worst answer of my career. I said, "Well, I can't explain that to you." Now, that sounds terrible, doesn't it? Here I am, a physicist supposed to understand these things, and I'm telling someone I can't explain a toy you give to children. But you see, the problem wasn't that I didn't understand magnets. The problem was much more interesting than that. So I'm going to try something here. I'm going to explain why magnets work in a way that I've never quite done before. And when we're finished, you're going to understand something not just about magnets, but about the whole business of asking why in physics. Because that's really what this is about. Let me start with something you already know. You've played with magnets. You've felt that push when you try to put two north poles together. You've felt that pull when opposite poles come close. It's a real thing. You can feel it in your hands. It's not like gravity, where you can't feel the earth pulling on an apple until it hits the ground. With magnets, you stick your hand between them and you feel something. There's clearly something there. Now, here's the question that gets everybody. What's there? What is actually pushing and pulling? You ask a child and they'll say, "The magnet does it." Okay, but how? They shrug. You ask an adult and they might say something about magnetic fields. Fine. But what's a magnetic field? They'll say it's the thing that makes magnets work. You see the problem? We're going in circles. The thing is, when you ask why about something in physics, you have to be very careful about what you're really asking. Because at some point, every why question hits a wall. And that wall is where the real interesting stuff happens. Let me try to build this up from scratch, the way I think about it. Everything is made of atoms. You know that. Atoms have electrons going around a nucleus. Now, I could tell you electrons are little particles spinning around in orbits, but that's not quite right either. Electrons are weird. They don't behave like little balls. They behave like probability waves. But for what we're doing here, let's just say electrons have certain properties, and one of those properties is something we call spin. Now, spin is a tricky word because it makes you think the electron is rotating like a little top. It's not exactly that. But it does have this property that we call spin, and this spin creates something. It creates a tiny magnetic field. Every electron is like a microscopic magnet all by itself. Think about that for a second. Every single electron in your body, in the chair you're sitting on, in the air around you, is a tiny magnet. So why isn't everything magnetic? Why doesn't your coffee mug stick to the refrigerator? This is where it gets interesting. In most materials, the electrons are paired up. One electron spins one way, its partner spins the other way, and their magnetic fields cancel out. It's like having two tiny magnets pointed in opposite directions, stuck together. From the outside, you see nothing. No net magnetism. But in some materials, iron being the famous one, you have electrons that aren't paired up. They're sitting there with their little magnetic fields, all by themselves. And here's the beautiful part. In iron, these unpaired electrons can talk to each other. Not literally talk, but through the way atoms are arranged in the crystal structure, these electrons influence each other. They prefer to line up, all pointing the same direction. Now imagine you have billions and billions of these electrons, all their tiny magnetic fields adding up, all pointing the same way. That's a magnet. That's all it is. A magnet is a piece of iron where the electrons have decided to cooperate, to all point their little magnetic arrows in the same direction. But wait, if iron atoms naturally want to line up, why isn't every piece of iron a magnet? Good question. Here's what happens. The electrons do line up, but they line up in little neighborhoods called domains. In one domain, everybody's pointing north. In the domain next to it, everybody's pointing east. In another, south. The whole piece of iron is broken up into these little magnetic neighborhoods, and when you look at the whole thing from outside, they all cancel out. What happens when you stroke a piece of iron with a magnet or put it in a strong magnetic field? You're convincing those domains to agree with each other. The boundaries move. The domain that's pointing the right way grows bigger. The ones pointing the wrong way shrink. Eventually, if you do it right, you get most of the iron pointing the same direction. Now you have a permanent magnet. And here's something wonderful. You can destroy this. Heat up that magnet, shake it around, and you're giving those atoms energy, jiggling them, randomizing them. The domains get scrambled again. the magnet stops being a magnet. You've turned ordered cooperation into thermal chaos. So that's part of the answer. Magnets work because electrons have spin. Spin creates tiny magnetic fields, and in certain materials those fields can add up instead of canceling out. But you're still waiting for the real answer, aren't you? You want to know why the electrons line up. Why does spin create a magnetic field? Why do opposite poles attract? Here's where I have to be honest with you, because this is the part that drives people crazy. When you ask why magnets attract, you're really asking, what is the mechanism? What's doing the pushing and pulling? With a spring, you can see the coils. With a rope, you can see the fibers. What's the mechanism for magnetism? The answer is that magnetism is the mechanism. It's one of the fundamental forces. It's not made of something else. Or rather, it is, but when you get to that level, you're talking about quantum electrodynamics, photons being exchanged, and then you have to ask what photons are made of, and you're off on an infinite regress. Let me try to say this another way. Suppose I tell you that electric charges create electric fields, and moving electric charges, which is what a spinning electron is, create magnetic fields. And these fields interact with other charges and currents. The math works out perfectly. We can predict exactly how strong the force will be, exactly where it will point, exactly what will happen when you bring two magnets together. We can design motors and generators and MRI machines and 1,000 other technologies, all based on equations that give the right answers every single time. But the equations don't tell you why there's a field there in the first place. They tell you what the field does. They tell you how to calculate it. They don't tell you what it is. And that's the deep thing about physics. At some level you run out of whys. You hit bedrock. And for magnets, the bedrock is, this is how the universe works. Electric charges exist. They create fields. Moving charges create magnetic fields. These are facts about reality, verified by experiment over and over and over. But asking why these facts are true is like asking why there's something rather than nothing. You can ask, but physics doesn't have an answer for you. Philosophy might, religion might. Physics just says, here's what happens, here's how to calculate it, here's what you can build with it. Now, I don't want you to think I'm giving up. I'm not saying it just works, don't ask questions. I'm saying something more subtle. The question, why do magnets attract, can be answered at many levels. At the level of domains and electron alignment, I can explain it. At the level of electromagnetic fields and forces, I can write down the equations. At the level of quantum electrodynamics, I can show you how virtual photons carry the force. But at each level, there's always another why underneath. And you know what? That's okay. That's actually beautiful. Because it means we're not at the end. There's always more to find out. Every answer opens up new questions. Here's what I find really interesting, though. The fact that you can feel magnetism at all, that you can hold two magnets and feel them push against each other through empty space, that tells you something profound about the universe. There's stuff going on that you can't see. There are fields permeating all of space. When you move a magnet, you're changing something everywhere around it, even in places where there's nothing but vacuum. Maxwell figured this out in the 1,860 seconds. He showed that electric and magnetic fields are really two aspects of the same thing. Change one, and you create the other. Shake a charge back and forth, and you create waves of electric and magnetic fields propagating outward at the speed of light. Those waves are light. Radio waves, X-rays, the glow of a fire, the warmth of the sun, all of it is electromagnetic waves. All of it comes from the same physics that makes magnets stick to refrigerators. When you pick up a magnet and feel it pull on a piece of iron, you're experiencing one of the four fundamental forces of nature. The same force that holds atoms together, that makes chemistry work, that allows you to see, that lets your neurons fire. It's all the same thing at the deepest level. So why do magnets work? Electrons have spin. Spin creates magnetic moments. In some materials, those moments align. Aligned moments create macroscopic magnetic fields. Those fields exert forces on other magnetic materials. Why does spin create magnetic moments? Because moving charge creates magnetic fields, and spin is a kind of angular momentum that behaves like moving charge. Why does moving charge create magnetic fields? Because that's what the electromagnetic field does. It couples to charge. It responds to motion. Why does the electromagnetic field exist? Because the universe has this fundamental thing called electromagnetism, one of 4 forces we know about, and it has these particular properties. Why does the universe have electromagnetism? I don't know. Nobody knows. Maybe someday we'll figure it out. Maybe there's a deeper theory that explains why there are 4 forces and not 5. Maybe the universe couldn't exist any other way. Maybe there are other universes with different forces. I don't know. That's beyond physics as we currently understand it. But here's what I want you to take away from this. When you hold a magnet, you're holding something that connects you to the deepest questions in physics. You're playing with one of the fundamental forces of nature. The same force that makes stars shine is what makes that magnet stick to your refrigerator. The same equations that describe subatomic particles describe the toy in your hand, and when somebody asks you why magnets work, you can give them a good answer about electrons and domains and fields. But then, if they keep asking why, if they keep pushing deeper, eventually you get to tell them the most honest thing a scientist can say: we don't know yet, but we're working on it. And that uncertainty, that not knowing, that's not a failure. That's the frontier. That's where discovery happens. The thing that made me love physics in the first place was exactly this. You start with a simple question, a child's question, and if you follow it far enough, you end up at the edge of human knowledge. You end up staring at the fundamental structure of reality. A magnet isn't just a toy, it's a window into how the universe is put together. So the next time you pick up a magnet, feel it, really feel it. That invisible push and pull, that force acting through empty space, that's something real, something profound. Something we understand well enough to use, well enough to harness, but still mysterious enough to keep us asking questions. And that, I think, is the most wonderful thing about it. We know enough to build the modern world, and we still don't know everything. There's still more to figure out. For me, that's not frustrating. That's exciting. That's why I do this. Magnets work. They work beautifully. And the fact that we can understand them as well as we do, while still having deeper questions to answer, well, that's physics. That's the whole game. You keep asking why until you can't anymore, and then you try to figure out how to ask better questions. That's what I was trying to tell that person who asked me about magnets all those years ago. I wasn't saying I didn't understand. I was saying that understanding goes deeper than they might have realized. And once you see that depth, once you really see how far the rabbit hole goes, you never look at a magnet the same way again. You know, there's something else I should tell you about magnets that most people never think about. When you see a compass needle swing around and point north, you're watching something remarkable. That little needle is responding to the Earth's magnetic field, a field generated thousands of miles beneath your feet by molten iron churning in the Earth's core. Think about that. A tiny piece of magnetized metal in your hand is connected, through invisible fields, to processes happening deep inside the planet. The whole Earth is a giant magnet, and your compass is having a conversation with it across thousands of miles of rock and ocean. And here's something that will really get you thinking. The Earth's magnetic field flips. Every few 100,000 years, on average, north becomes south and south becomes north. We know this because when lava cools and hardens into rock, the magnetic minerals inside it freeze in place, pointing toward wherever magnetic north was at that moment. Geologists have mapped out these reversals going back millions of years. The rocks remember. They're like a tape recording of the Earth's magnetic history. And right now, as we speak, the Earth's magnetic field is weakening. Maybe it's getting ready to flip again. Maybe not. We don't know exactly when or how fast these things happen. But the magnets in your kitchen, they're part of the same story as continental drift and volcanic eruptions and the slow churning of our planet's iron heart. Let me tell you about something that confused physicists for a long time. Why is iron magnetic, but copper isn't? They're both metals. They both have electrons. What's special about iron? The answer has to do with the detailed structure of atoms, the way electrons fill up their energy levels. In iron, and a few other elements like cobalt and nickel, there's a particular arrangement where you end up with unpaired electrons in a shell that's tucked inside the atom. These electrons can interact with their neighbors in just the right way to prefer alignment. It's a quantum mechanical thing, really. The electrons in iron are in a kind of Goldilocks situation. Not too tightly bound, not too loosely bound, just right for magnetic ordering. Change the elements slightly, and the magic goes away. I remember once explaining to a student that magnetism is, in a sense, a relativistic effect. He looked at me like I was crazy. Magnetism, relativistic? But it's true. If you have a wire carrying an electric current, and you put a charged particle next to it, that particle will feel a magnetic force. But here's the strange part. If you run alongside the particle at the same speed, so it looks stationary to you, you don't see any magnetic force anymore. Instead, you see an electric force. The magnetic force transforms into an electric force depending on how you're moving. Einstein showed that electricity and magnetism are really the same thing, seen from different frames of reference. What looks like magnetism to one observer looks like electricity to another. They're unified. They're one phenomenon with two faces. This is why we call it electromagnetism, not electricity and magnetism as separate things. Maxwell unified them mathematically in the 1860 seconds, but it took Einstein in 1905 to show us why they had to be unified. Special relativity demands it. The structure of space and time requires that electric and magnetic fields transform into each other when you change your motion. So when you play with a magnet, you're not just playing with some isolated phenomenon, you're holding a piece of the relativistic structure of the universe in your hand. Now, let me tell you about something practical, because I know some of you are thinking, this is all very nice, Feynman, but what can I do with it? Fair enough. Let's talk about electromagnets. You take a piece of iron, wrap a wire around it, and run current through the wire. The current creates a magnetic field, the iron amplifies it enormously, and suddenly you have a magnet you can turn on and off. That's how electric motors work. That's how generators work. That's how the speaker in your phone vibrates to make sound. Every time you listen to music, you're using electromagnetism. The signal comes in as an electrical current. It goes through a coil. The coil creates a magnetic field. The field pushes on a permanent magnet attached to a membrane, and the membrane moves air, creating sound waves. It's beautiful engineering, and it all comes from understanding how electrons and fields interact. Here's another thing that surprises people. Light is an electromagnetic wave. When you see red light, you're seeing an oscillation of electric and magnetic fields at about 400 trillion times per second. Your eye has evolved to detect these oscillations, to distinguish different frequencies as different colors. Radio waves are the same thing, just oscillating much slower, maybe a few million times per second. X-rays oscillate much faster, trillions upon trillions of times per second. It's all the same phenomenon. Maxwell realized this in the 1860 seconds, and when he calculated the speed of these electromagnetic waves, he got the speed of light. That was how we discovered that light is electromagnetic radiation. That was one of the great unifications in physics. Light, electricity, and magnetism, all the same thing. You want to know something that still amazes me? Permanent magnets stay magnetized for years, decades, sometimes centuries. How? Why don't the domains scramble back up? The answer is that it takes energy to flip those electron spins, to break the alignment. At room temperature, the atoms are jiggling around, sure, but they're not jiggling hard enough to overcome the forces keeping the electrons aligned. It's like a ball sitting in a valley. It might shake a little, but it won't spontaneously jump over the hill unless you give it enough energy. Heat the magnet up, and you give those atoms enough energy to randomize. Cool it back down, and it might stay random unless you magnetize it again. There's a temperature called the Curie temperature where magnetic order breaks down completely. For iron, it's about 770 degrees Celsius. Above that temperature, iron loses its permanent magnetism. It becomes just another paramagnetic metal. I should mention superconductors because they do something truly strange with magnetic fields. When you cool certain materials down to very low temperatures, they become superconducting, zero electrical resistance. But they also become perfectly diamagnetic. They expel magnetic fields from their interior completely. If you put a magnet above a superconductor, the magnet will float. It levitates. The superconductor creates currents on its surface that exactly cancel out the magnetic field inside, and those currents push back against the magnet, holding it up in midair. It looks like magic. It looks like science fiction. But it's just physics. just electrons doing what electrons do when you get them cold enough. We use this effect in maglev trains, in MRI machines, in particle accelerators. The universe gives us these phenomena, and we figure out how to use them. One more thing, and this is maybe the most important thing I can tell you. All of this, everything I've described about magnets and fields and electrons and relativity, all of it comes from asking simple questions and refusing to accept vague answers. When somebody tells you magnets just attract, push back, ask how, ask why. Keep asking until you get to something real, something you can test, something you can calculate. That's what science is. It's not a collection of facts to memorize. It's a way of thinking, a way of refusing to be satisfied with hand-waving and mysticism. The universe is comprehensible. It follows rules, and those rules are beautiful when you see them clearly. Magnets are just one example, one doorway into that beauty. Walk through it, and you'll find a whole world of wonders waiting for you.